We all kind of think of the Earth as this solid rock, right? Stable ground under our feet. But what if that's just a phase, an illusion even? What if the planet's real default setting is just constant chaotic motion? We're going to dive into that because a huge volcanic eruption just showed us this incredible, shocking link between the air and the ground, and it's making us rethink, well, pretty much everything.
Okay, so it all kicks off with this monster eruption, the Hunga Tonga volcano back in January 2022. We're talking the biggest volcanic explosion we've ever recorded with modern instruments. And it did something that just sounds impossible. This quote from Ken Macpherson at the University of Alaska Fairbanks really captures it. The pressure waves from the air literally shook the ground in Alaska. That's 6,000 miles away. Just think about that for a second.
So yeah, that leads to a pretty big question, right? How can an explosion in the South Pacific make the ground, kilometers deep, shake on the other side of the world? I mean, this wasn't your typical earthquake sending tremors through the rock. No, this was a wave in the atmosphere that somehow managed to rattle solid Earth. How does that even work? All right, to figure that out, we've got to look at this really surprising, totally invisible connection between the air and the ground. It's like a ripple that went right across the whole planet. The answer has this kind of cool name, air-to-ground coupling. And honestly, it's pretty much what it sounds like. The air itself is dumping energy straight into the ground. And this isn't some wild theory, okay? It's a real, measurable thing that just goes to show how deeply connected everything on our planet really is. So, here's how it works, step by step. First, that huge eruption creates these massive pressure waves in the air. Simple enough. Then, as these waves zip across the globe, they're actually pushing down on the surface of the Earth and then pulling it back up, like a giant, invisible hand. And finally, all that pushing and pulling transfers energy deep, deep into the crust, and that generates brand new seismic waves. The air literally made the ground shake. What this really tells us is that our planet isn't just a bunch of separate parts, atmosphere over here, rocks over there. No, they're in this constant conversation. And the Tonga eruption, that was just that conversation suddenly turning into a shout, so loud we couldn't ignore it. And that idea, that connection, is going to lead us to something even bigger, about how our world is actually built. Yeah, this whole idea of a connected, always moving planet makes you want to look deeper, right? Not just at one volcano, but way back into the ancient, super slow-motion processes that actually built the continents we live on. I mean, think about it. Our continents have been around for billions of years, these incredibly stable platforms for life. But how? What was the secret sauce? What does it actually take to build a continent that can last that long? While the answer, believe it or not, is just insane heat. We're talking temperatures down in the lower crust getting hotter than 900 degrees Celsius. That's way hotter than we used to think. It wasn't just warm, it was a literal planetary forge. So how does crazy heat make something stable? It's a bit counterintuitive, but here's the recipe. Go back about 3 billion years, when the whole planet was way hotter. That heat made the deep crust almost like a thick liquid. This allowed all the radioactive stuff, uranium and thorium, which generate their own heat, to kind of float upwards. But getting that heat source out of the depths and up to the surface, the deep crust could finally cool down, get stronger, and lock into place. And voila, you have stable continents. And this discovery is completely flipping our old ideas about the early Earth upside down. We used to think that a hotter Earth meant the crust was more rigid, a stagnant lid they called it. But these new models, especially one that looks at how rock actually gets weaker when you stress it out, they suggest the exact opposite. They predict a sluggish lid, a planet that was always mobile, just with this weirder, more chaotic, kind of drippy style of plate tectonics. Okay, so if our own planet started out with this weird, sluggish, always moving crust, what does that mean when we look for life out in the universe? It makes you ask a really wild question. What if life doesn't even need continents to get started? For so long, our search for life has basically been a search for another Earth. We look for planets with continents, with oceans, with the right kind of geology to keep the climate stable. But what if that's just us being biased? What if that's not the only way to build a habitable world? Let's compare the two paths here. On a planet like Earth, staying habitable is a full-time job. It's this active balancing act of geological cycles. But now imagine a water world, a planet totally covered in a super deep ocean.
The immense pressure down on the seafloor basically shuts those cycles down. So for them, habitability isn't an ongoing process. It's something that gets baked in, right from the start, based purely on the planet's starting ingredients. And the crazy part is, it works. The models are showing that a good chunk of these water worlds, maybe a quarter of them, could stay habitable for more than 1 billion years, all without any of our familiar geology. This just blows the doors wide open on what we should be looking for out there. And thinking this broadly about what makes a planet work isn't just for finding aliens. It's super important for our own future, for humanity's future in space. Because if we're going to go anywhere, we need to understand the geology of other worlds to find the one thing we absolutely can't live without: water. And that's a huge challenge, right? We need that water, but it's not always in the obvious places. Look at this. Mars, yeah, lots of potential for ice under the surface, a pretty good spot to set up shop. But Mercury, the planet literally roasting next to the sun, it has huge chunks of ice hidden in dark craters. And then our own moon has surprisingly little. Understanding why it's like that is everything if we're serious about exploring. All right, let's bring this all home. We started with air shaking the ground. We saw how continents were born in a planetary fire. We've even considered that life might not need land at all. All these threads, they're weaving together to point to one last, really big idea about the era we're in right now. There's this philosopher, Thomas Nail, who says we've just been looking at our planet all wrong. We like to think of it as this system that's always trying to find balance, trying to be stable. But he says no, its real nature, its default state, is turbulence. It's a system that's always operating way, way out of balance. And that brings us to this idea of the Holocene. Think about it. The last 12,000 years or so, the Holocene has been remarkably stable. It's the period that allowed all of human civilization to happen. The Holocene theory says that period, that was the fluke, that was the exception. And now, we're heading back to the planet's baseline. We're entering an age defined by what's normal for Earth: motion, turbulence, and really fast change. So where does that leave us? With a huge final question. That volcanic shockwave, the way our continents were made, the chaotic ancient Earth, these aren't just history lessons. They're hints about what our planet is really like. So if that stable world we got used to was just a short vacation, and the planet's normal state is constant motion and turbulence, how do we adapt? How do we learn to live not just on the Earth, but with it?